In this problem, I have the picture on one page and then the parts on the other. So it wants us to draw and label the electric field at point P due to each of the two negative Q1 charges and express the net electric field at the origin in figure A in terms of KQ1 and A. And then it wants us to do the same thing for the line of charge. And then it wants us to draw and label it due to the Q charges and the line of charge, and using the sum of the answers of A and B to express the net electric field. And then it wants us to set the charges equal and then find the length that would make the electric field at the origin 0. So let's start with point A. So first we need to draw the electric field at point P due to these two charges. So here is negative Q1 and here is negative Q1. So that means equal charges, that's great. They're equidistant away in the y direction and then in the x direction, so that's helpful. So if I'm going to draw at P, the at P, so I'm going to put the tail of my vector here, and I'm going to draw it towards Q1, right? And then I'm going to do the same thing here. This is the field is going to be towards this Q1. So these should be equal because the charges are the same and the distance away, that hypotenuse, is the same for each. Now looking at these, right, this vector right here is composed of a negative x component and a positive y component, and this vector is composed of a negative x component and this is a negative x and a positive y, this is a negative x and a negative y. So the y components cancel and I'm left with two of the x components. So the net is going to look like that. So that's going to be my F net. And we'll call that 1 net. And now I need to do a calculation. So I think I'll do that on this page. So my F, or my E, is going to equal, I'm going to have the x component due to each of them, and those are equal. So I'm going to need to say 2, so 1 for each of them, and then k q1 over the distance away is going to be this distance, right? So we'll call that, just for now, r1 squared, but it's the hypotenuse here, right? And times cosine theta. So because I'm taking the x component. Remember the 2 is because I've got 2 of them, and since they're equidistant away, my equation is going to be the same, kq1 over r squared. Charge is the same, distance away is the same. So if I think about what my r1 is, my r1 is the distance from P to my charge, and I can see that that's a right triangle, right, with side A, square root of 3a, and then I need to find the hypotenuse. And I know this is, looking at it, it's a 1, 2, square root of 3 triangle, but we can figure that out too. So if I just draw this triangle, now it's a right triangle, sorry my drawing's not that great, but this is, say, A, this is a square root of 3a, so what's my hypotenuse? Well, I can just say hypotenuse squared is equal to a squared plus square root of 3a squared. Right, so when I square them, I'm going to have h squared is equal to 4a squared. So h is going to equal 2a. So this is going to be 2a. Right, so up here, then I can say this is going to be 2k q1 over, so my r squared, right, is the distance from here to here, so that's going to be 2a squared. And then cosine theta, here's my angle. Cosine theta is adjacent over hypotenuse. So cosine theta is a over 2a. So that's going to give me, these 2's cancel. I still have my 4 on the bottom. So I'm going to have, let's see, k q1 over, one of the a's cancel, so I'm going to have over 4a. Let's just check and see if I get that right with my notes. Okay, is that making sense? My hypotenuse, A over 2A, that looks right. So I'm going to say that that's equal to, E is equal to KQ1 over 4A I have 4A squared because this A and this A cancel. So it should be squared. 4A squared in the negative I hat direction. That's my vector. Okay, so remember it goes to the left. Do we have everything? We have our 2 for 2 charges. We have our R, which is 2A, so that's 4A squared. And then we have our cosine theta, which is A over 2A. A over 2A, that looks right. Okay, so now we want to consider this piece. So here I've got a charge, a line charge. It's finite, so it has a length L, and I need to figure out the electric field. So I need to use an integral. So I'm going to say here E. So let's do this. dE. Let's look at a little electric field at point P due to, say, this little bit of charge. So I'm just going to like imagine if I just chunk this up into this tiny little bit of charge, and then my integral is just going to add them all up. So I need to find the electric field due to that little bit of charge at point P. Now notice my Q2 is negative, so that I have a negative Q2, so that means my electric field is going to point this way. So it's going to be pointing in the X direction, and I'm going to get a little bit of E at each of these from each of these charges at P, so we'll add them up. So that's what an integral does, right? So I'm going to have K dq over R squared. Okay, well, let's think about this. We have this line of charge, and so we're going to use our lambda. So if I think about lambda, lambda is equal to Q, the charge, over L. So I can say d lambda is equal to, or sorry, so let me undo that. So now if I say, all right, Q over L, and then if I say Q is equal to lambda L, then that means that dQ is equal to lambda. So lambda always stays the same, right? And this is going to be dx, right? So I'm moving in the x direction just a little bit at a time, and I can substitute dq is equal to lambda dx over here. And then r is the distance from P to each of the little charges. So I'm going to call r now x. So I'm going to say this is equal to k lambda dx over x squared. Oops. Rewrite that. K lambda dx over x squared. So that means E is going to equal the integral of k lambda dx over x squared. And I'm going from, back over here, I'm going from A, the distance away from P is A, to A plus L. So those are going to be my limits. I'm integrating it from A to A plus L. Now looking at this, K and lambda are constant, so I can pull them out of the integral. And I just have the integral from A to A plus L of dx over x squared. And so that's the same as the integral of, keep the limits the same, but that's really just x to the minus 2 dx. So I can use the formula, right? That the answer to that is x to the n plus 1 over n plus 1. So that means that's going to be x to the n plus 1. N is negative 2, so negative 2 plus 1 over negative 2 plus 1, which is going to be x to the negative 1 over -1. So I can rewrite that E is equal to K lambda, and then, so x to the -1 is 1 over x, right? And -1, I can say this is negative. So I'm just going to put the negative outside from this negative. And I'm evaluating from a to a plus L. Okay, so that's going to be E is equal to K lambda. And substituting in, I'm going to have 1 over a plus L minus 1 over a. Okay, now I can substitute back in for lambda. So I'm going to say E is equal to K. So remember, lambda is equal to Q over L. So I'm going to have Q over L. I forgot my K. And I'm going to get a common denominator here. So I'm just going to multiply the two together. So I'm going to have A and A plus L. And when I do a common denominator, since I added the A here, I have to add it on top over here. So I'm going to have the A. I had to multiply both top and bottom by A to get the common denominator, so A. And then over here, I had to multiply top and bottom by A plus L. So that's going to be minus A plus L. And so that's going to equal K Q over, and I'm forgetting my negative here, my negative here, my negative here, KQ. Now the A's cancel, but I'm left with a negative L. Right, this A cancels with this A, but this negative distributes through to the L, so I get the negative L, and then over A plus L. And I have an L over here too, that I bring down. So my negatives cancel, and then my L's cancel. And I'm left with E equals K Q over A plus L. Let's see if that seems right from my notes. Oh, I forgot my A here. Where is it? I forgot this A, so I need an A here. I didn't bring that down with me, so I've got an A. There we go. I knew it was wrong because I didn't have a, I knew I needed a squared term down here in order for the electric field to be right. So this is going to be in the positive I direction. Right, so this is my E field for the two charges. This is my E field for the line of charge. So I've done A and B in this, and I've drawn it both on here too. And C says, draw and label the fields due to each of the 2-point charges in the line of charge. Use the sum and express the net electric field at the origin in figure C in terms of those variables. Okay, so let's just look at this. And I can draw it right here. So I know that, well, maybe we'll make a new drawing, but I know that there's going to be a force to the left due to these 2-point charges and a force to the right due to the line of charge. So if I want to draw that for C, let's go C. This is going to be my Y. This is my P. And this is going to be force 1. Sorry, this is force due to 2. See if I can erase that. This is due to the line. And this is going to be my force 1, and that's due to the charges. So charges, line. This is P. Okay, so we want to see what the E total is. E total is equal to, if I go back, I need this one, KQ1 over 4a squared. So KQ1 over 4a squared. And this is in the negative direction, so this is this one. And then the other one is KQ over a times a plus l. So KQ2 over a times a plus l. Right, and this is all in the positive I direction. And why do I know it's positive? I mean, I don't, but I'm saying this is the positive direction. This is this one. That's the positive direction minus this one. And if, when I calculate this out, if given A's and L's, I would find out which of these terms is bigger, and that would change. If this is bigger, it's going to stay positive. If this one's bigger, then it's going to go negative. So there, we've done C, right? So we've got K, Q1, Q2, A, and L. Great, and now D. It's saying for D, let's do D up here. If L equals A in this equation, then find the ratio so that the E field is 0 at the origin. So at here, we want these two to be equal. So I can just set these two terms equal. I can set L equal to A and then solve for Q1 over Q2. So let's do that. So we'll say K Q2 over, now I'm plugging in A, and then since now L is equal to A, we're going to make that 2A, equals KQ1 over 4A squared. Now I can cancel out my K's, I can cancel out my A's, and I'm left with Q2, or let's do, yeah, Q2 over 2 is equal to Q1 over 4. So if I want Q1 over Q2, I'm just going to bring Q1 down, Q2 down here, and I'm going to bring the 4 up there. So I'm going to have 4 over 2 is equal to Q1 over Q2. So Q1 over Q2 is equal to 2. So that's D. And the bonus. So for the bonus, we do the same thing, right? We find L such that, so now we're given Q's, that what Q1 is, so we can plug in Q1 is equal to 2Q2, and then we solve for L. So let's do the bonus. So we're going to say KQ2 over A times A plus L is equal to K, and now we're plugging in for Q1, for this Q1, we're going to plug in 2Q2. 2Q2 over 4A squared. Okay, so the K's cancel, the Q2's cancel, and A cancels. So I'm left with 1 over A plus L is equal to, so I can factor out a 2 here, this goes to a 1 and this goes to a 2, is equal to 1/2. So cross multiply and I get A plus L is equal to 1/2. So L is equal to 1/2 minus A. See if that makes sense. So I think I'm missing an A here. I've canceled out an A, but I think I still have an A. So I think I actually have 1 over 2A here. That makes a lot more sense. So, hold on, I think, so I need an A here. Yeah, all right, so let me go back. So 1 over A plus L is equal to 1 over 2A. So then I can cross multiply. So I'm going to have A plus L is equal to 2A. Sorry, I get these weird lines coming in on me. So now L, subtract A from both sides, and I get L is equal to A. So that's my bonus. And let me erase over here too. This is equal to 2.